Welcome, teachers. My name is Erik de Schrijver. I'm a high school teacher of physics and chemistry at St. Peter's College Jette in Brussels. Final years of secondary education. I am by training a physicist. I hold a master's degree. Okay, the Asgard program is pretty much in its 11th year now. And what we're trying to do is to run a program along the same lines as what space agencies do when they fly space missions. So it's not like a CANSAT competition. It's more like an ESA or NASA space program where NASA decides, for instance, to fly a planetary probe to Jupiter, and then asks the scientific community in the United States and worldwide for project proposals. Spaceflight. Let's assume that most of you, if not all of them, have some scientific background. Space is a place, and you can go there without having an object put into orbit. So once you cross the Kármán line at 100 kilometers, you are in space. But in order to stay there, you will need to achieve orbit, which means you will need a satellite. That, however, is a quite expensive proposition, as the launch of a CubeSat is on the order of several tens of thousands of dollars or euros, whatever. And that is without even making mention of the technical difficulties of producing hardware that is qualified to survive the launch. Surviving orbit is hard enough, surviving the launch is even tougher. So that is, in my opinion, not exactly a viable proposition for pretty much all high schools worldwide. There are some notable exceptions in the United States. High schools have been launching CubeSats, but these tend to be private schools for children of extremely wealthy individuals, not the kind of schools we are familiar with in Europe. They have some in the UK, but so let's rule out the CubeSats. If you still want to go in space, the other option would be to use a sounding rocket, which reaches an altitude of 100 kilometers or more. That is significantly cheaper, but it still comes at a price that is pretty hefty. And of course, there's a trade-off here that the flight duration is very limited, typically on the order of 15 to 20 minutes at the most. Still talking about several thousands of dollars per kilogram. There's not really a market for it. It's basically a kind of mission that is comparable to a CANSAT on steroids. I mean, it goes way higher than CANSAT, but it's very short. It does reach interesting altitudes, but the number of flight opportunities are extremely limited. Balloons, however, have the advantage of reaching near space, which is a quite impressive altitude, even if it falls way short of the Kármán line at 100 kilometers. And these balloons basically fall into two categories. The one you can see on the left is used for scientific ballooning. These balloons carry payloads of several hundred kilograms up to several tons. There have been payloads of over 5 tons. Flying on this type of balloon. They're not all that common. They're mostly flown by either the Swedish Space Corporation from Kiruna in Sweden. The French Centre National d'Études Spatiales flies several a year over Antarctica and different places all over the world. And the major operator of these scientific balloons is Columbia Scientific Ballooning Facility, which is a part of NASA in the United States. They also fly worldwide. Similar altitudes, however, but with smaller payloads, can be obtained with weather balloons, and these are, as far as space programs go, extremely cheap, costing a few hundred euros, which allow you to fly payloads of a few kilograms to altitudes that are absolutely comparable to the bigger balloons, and we're talking 30 to 35 kilometers here. So that region is typically referred to as near space, and it's way short of the Kármán line. I mean, 30 kilometers is nothing like 100, but then most physical parameters that are varying between sea level and space are not varying linearly, but exponentially, and that means that at 30 kilometers, altitude, you actually have only 1% approximately of atmospheric pressure, for instance, compared to what you have at sea level. So if you look at Earth's atmosphere, a lot of changes are taking place in the lower 30 kilometers. All weather phenomena are taking place in the troposphere, which is the lower, say, 12 kilometers. And our balloons at 30 kilometers are deep into the stratosphere. Very dry conditions there, practically no water vapor in the air, very high UV radiation levels, very low atmospheric pressure, conditions that are not like they are in orbit, but they go a significant way. So there's a lot of things that can be measured to change between sea level and those altitudes, making it interesting for a wide variety of scientific experiments, going from the obvious temperature, pressure, all the way up to more sophisticated measurements, radiation, behavior of radio waves, and things like that. This is actually a picture that was taken by students from Atheneum Willebroek a number of years ago. These students were in the 3rd year of secondary education, so that would be something like, yeah, what would that be? 9th grade, I think, if you use the Anglo-Saxon counting system. It was taken over Brussels, and if you look at the lower left corner, you will see the docks of Antwerp Harbor. I don't know if you guys can see my cursor, but this would be Antwerp Harbor. You have the English Channel over here, and the great patch you see near the horizon there is actually part of the UK. So you have quite a line of sight from these altitudes. And of course, the main things that are striking in this image is how dark the sky is, that Earth is indeed a blue planet, and that if you look carefully at the horizon, you can see that Earth is a sphere. So you begin to see the spherical nature of the globe. Okay, so here's a comparison that is also quite motivating to students. That is that at Asgard altitudes, you can actually test quite a number of things technologically under conditions that are similar to those on the surface of Mars. I mentioned low pressure, UV radiation, lack of water vapor in the air, and the temperatures. Temperature is dropping with altitude in the first few kilometers of the flight up to the time the balloon reaches the troposphere, which is just below the airplane you see on the left figure. Actually, temperatures go back up after that, but it becomes somewhat harder to measure because air density is getting so low that heating and cooling processes are more radiative than convective. So actually, it becomes quite hard to measure temperatures like that. And what you're measuring most often is the temperature of the thermometer, not the temperature of the air, just because there's not enough air. And you don't stay at these altitudes very long. So it's quite hard for a thermometer to reach thermal equilibrium with the environment. But still, the measurements we have performed over the years are quite consistent with what is in the scientific literature. So it's feasible. It's just that you should be aware that measuring things at these altitudes may not be all that obvious. Okay, so how does an Asgard campaign work? We invite primary schools from Belgium to send in a project proposal, and secondary schools worldwide for a project proposal by November 11th. Okay, it's always November 11th, year after year, armistice, that's a benchmark. And we have a jury led by Belgium's first astronaut, Viscount Dirk Vriemhout, to help us select the best project proposals. Viscount Vriemhout is eminently qualified to do so, having spent a big chunk of his career developing scientific instruments for high altitude ballooning. So he's quite aware of what is feasible, not feasible, what is well and what is not. There are other people in the jury who are advising him and the other jury members on what is feasible at school level, because what may be scientifically feasible may not be feasible at school level, or vice versa. We then communicate to the teams before Christmas holidays start whether their project has been selected and under what conditions. I mean, a team can be selected for a project proposal, but ask for a total mass of, say, something like 200 grams. If the jury thinks you can do it for less than 100, we will select the project and give you a mention that we think you should make efforts on cutting back on the mass. Cutting back on mass is a permanent concern, because obviously the payload capability of the balloon is limited. And if teams start making experiments that are too heavy, then not every selected experiment can be flown. So everybody needs to be quite disciplined and mindful of the constraints imposed by the jury there. But before Christmas exams are over, or before Christmas holidays start, the teams will be notified of their selection if they are, or non-selection if they are not, which gives them time from December pretty much to March, early April, to design, build, and test their experiment. I mentioned design, build, and test because experience has taught us that an experiment that has not been tested is quite likely to fail, for whatever reason. It could be a short circuit, it could be wires breaking loose, it could be batteries not having enough capacity because the cold affects that negatively. It could be a whole host of reasons why experiments don't work, so testing is absolutely necessary. And then in April, we have a 3-day launch campaign, after which we will expect the scientific teams, the different school teams, not the primary schools, obviously, but the other teams to produce a scientific poster in English. These posters are intended for the website, of course, but they are also intended from an educational point of view to teach the students how to write a paper, how to present scientific data, how to provide that scientific data in a visual form that is at the same time scientifically correct, convincing, and compelling. Okay, we do make a distinction between beginners teams and more advanced teams, because obviously once you have participated in Asgard once, you will know pretty much how it goes. You will have learned a number of valuable technological lessons. And that advantage pretty much rules out new schools from entering the project just because the other ones are so much more experienced. So in order to guarantee schools with no prior Asgard experience to still be able to participate, we reserve a number of slots to schools that have little or no Asgard experience yet. Obviously, in the slide here, it is mentioned that the beginners are schools that have little or no Asgard experience. Advanced are schools with 2 years of more experience. Obviously, this refers to the teacher, not the students, who mostly just participate once. But still, they're allowed to participate several times. That's not the question. But the experience resides with the teacher, so it's his or her experience that we will be counting on deciding whether or not your school is experienced or advanced or not. Okay, in the months between the selection of a team and the date that you will be required to provide us with the hardware of the flight, there are two moments in time where we will expect a progress report. That's not supposed to be a big bunch of paper detailing everything you did, but we should know or we should be able to determine from that report whether or not you're still on track and on schedule to provide working hardware by the time we need it. There's technical support available by me or by the other teams, because as Asgard is not a competition, you don't need to be hesitant about turning to other teams for counsel or experience or advice, whatever. Once you are selected, your slot on the balloon is secured. And basically the only thing that can happen that would stop you from flying is by not complying with the constraints of the mission. So it's not like you have to prove anything other than to yourself that you are able to provide the hardware that you proposed would be your experiment. There's an Asgard community on Facebook. There's technical information going on there. There's also practical information. I would urge every one of you to go and have a look at it. It's called Asgard 11 right now, 11 in Roman numerals. So that would be definitely a place where either you or one of your team students should adhere to keep track of what is going on. There's updates posted there on, for instance, the type of connector we're going to use to connect scientific experiments to the common Asgard batteries. If you have any specific questions regarding the campaign or regarding your or other experiments, that would be a good place to do. We had an experiment a number of years ago that pertained to the electrical field of the Earth. And obviously that team wanted to make sure that there were no other experiments in the immediate vicinity of theirs that would produce electric fields that might negatively impact the quality of their measurements. These sort of things can be discussed on the Facebook group, or you can send your questions to me if you prefer doing that. We do not wish you to feel abandoned. The goal for everyone, and that includes me, of course, should be to make sure that the flight is a success for your team. So absolutely do not hesitate to ask for help if you run into any kind of trouble or if you feel insecure or unsure about anything. Okay, well, it's probably interesting for you guys if you feel like participating in Asgard. Examples of project proposals that have been flown in the past by teams that had no prior experience in Asgard. My own team, when Asgard just started, got into experiments like this until the time that we got to master the art of using microelectronics and microcontrollers to actually do some physics. I'm not a biologist myself, so this was not my preferred type of experiment, but there can be some really interesting scientific results coming out of this. So you can fly plant seeds, for instance, keep a control group on the ground, fly some seeds, and then check afterwards if the seedlings grow at the same rate, if there's any deviations, things like that. Pretty basic. If there are differences, I'm pretty sure you cannot distinguish what parameters did cause that. Was it the cold? Was it UV radiation? Unless, of course, you divide your experiment into different sets of seeds, some of which you expose to the near vacuum, some of which you expose to UV radiation, but not the near vacuum, some of which you expose to the cold and UV, but not the near vacuum. All sorts of combinations can be made. We've had teams sending UV sensitive paper wrist, what do you call them? It's a kind of thing you wear around the wrist to detect UV radiation to make sure you don't burn or you get a kind reminder to apply some sunscreen. You can design experiments with that. You can go to an aquarium shop and buy some Artemia salina eggs. Artemia salina are brine shrimp. They sell them in aquarium shops in the form of eggs, and these eggs are dry. So you can send these eggs up and then see if upon the return of the balloon, they still hatch at the same rate, if the growth process of the Artemia is the same or if there are any difference there. We've had quite a number of schools flying agar substrates to the edge of space, see what that does to bacteria, see if you can catch any bacteria up there, although that would require some mechanism to expose the substrate to stratospheric conditions without exposing it at lower altitudes. But still, you can send some agar substrate that you have contaminated with bacteria here on the ground, and then see what happens to those bacteria after an exposure to UV radiation, low temperatures, low pressure. You see some examples here of the different stages in the growth cycle of Artemia. The eggs are about 1/10 of a millimeter in diameter, so you can literally have a very, very lightweight experiment and still send like 1 million eggs up there. A full-grown Artemia is about, I don't know, centimeter in size, and it takes a couple of weeks for them to grow. So you have plenty of time to study their growth cycle with the students. It's not like they're full grown within 24 hours or anything. There's plenty of time to do measurements. Advanced teams have been flying experiments very highly concentrated on the use of microelectronics. Arduino is quite popular. Raspberry Pi is gaining in importance over the years. Although I must say we are not extremely fond of Raspberry Pi because it tends to be very power hungry. It draws a lot of current, and that means we need a lot of batteries, and batteries are heavy. So if you guys are thinking about submitting a project proposal that is based on electronics, I suggest you check if it is feasible on Arduino, which is lightweight and not very power hungry, rather than going to Raspberry Pi. We can consider Raspberry Pi, make no mistake, but if the sensor can be operated from an Arduino, there's no point in putting a power hungry Raspberry Pi up there. It just draws too much current for that. But if you want to do something that Arduino cannot handle because the volumes of data are too big, for instance, or because you need a considerable amount of computing capability, then Raspberry Pi may be the only way to go, and we will definitely consider it. So what experiments have been flown by the experienced teams? There's a motorcycle passing by. Okay. What experiments have been flown by the more experienced teams? Well, we've had teams that would bounce off radio waves on the ionosphere and then see where on the ground they could be detected. My own teams of students have been working on detecting atmospheric gamma radiation in recent years. We have flown numerous Geiger counters in different configurations to gain some insight into the angular distribution of the radiation and possible changes of that with altitude. We've flown solid-state particle detectors with and without lead shielding last year. And recently also we have started flying gamma spectrometer to see what the energetic distribution of the gamma photons look like and how that changed with altitude. We've had teams from abroad taking samples of stratospheric air and trying to trap some stratospheric bacteria in there. We've had measurements of the speed of sound as a function of altitude. It changes not that much, but there is a change there, and it's not too hard to measure. It's harder to make an interpretation of what is going on, but the hardware is feasible. It's not all that easy, but it's quite feasible. We've had measurements of UV intensity, and there's probably a lot more that I believe in. So there's plenty of possibilities. Okay, here you see some data that my students obtained with Geiger counters, and in the lower right, for instance, you can see that the vertical radiation is topping the horizontal radiation at altitudes below, say, 15 kilometers. You also see that in both cases, there's a maximum in radiation intensity that is known in the literature as the Pfotzer maximum. Some people arguing for changing that to Pfotzer-Wegener, not mentioning only the professor, but his assistant as well. And then the situation more or less reverses once you cross the 20-kilometer mark. So this is obtained with a Geiger module that is connected to an Arduino. This is hardware that you can purchase. You need to provide your own software for an experiment like this. But as a physicist, I thought this was quite nice. See results like this. Okay, what can you expect from the launch campaign? It lasts 3 days, and what we are offering is this. We are starting on a Wednesday morning. It's always on a Wednesday morning that we start, and we start at the planetarium with teams making presentations to each other. So each team prepares a 10-minute presentation on their project, the problems encountered, the hardware build, the results they hope to obtain. These presentations are given in English, obviously, as we have teams coming in from different countries. We also provide a guest speaker. Professor Catherine Kohlenberg, who is attending today, was our guest speaker a few years ago. Last year, the presentations by the invited speakers, of course, were given online. The whole campaign was virtual. But we hope to do a physical campaign this year. We'll see how it goes, but we definitely holding out hope that we can do it physically as we did before this pandemic hit. We provide these invited speakers just to break the ice, so there's no single student team that needs to have more stress than they probably will have speaking in public. And it's interesting for the different teams to know what the other experiments are about. It also helps see that there are worldwide students with similar interests and motivations and aspirations and ambitions. That is for Wednesday. We have a number of images here taken from such a day. This mentions we do payload integration on Wednesday afternoon. I need to correct that. We do payload integration now 2 weeks prior to the flight. So that means you will need to provide us with the hardware for your experiments about 2.5 weeks prior to the launch date. The reason is that as we fly 2 balloons now, the number of participating teams has grown. That means that the time we need for the presentations on Wednesday is somewhat longer, and that does not leave enough time to integrate all these experiments in a quiet and efficient and reliable way. So we do it 2 weeks prior to the campaign so that there's no undue stress, because stress induces human error, and that's not something we want. You guys have worked hard by that time to make your experiment work. We want you to fly in the best possible conditions. So Wednesday we do presentations. Thursday is launch date. We convene at the site of the Space Pole. That's where the Royal Meteorological Institute, the Royal Observatory, and the Belgian Institute for Space Aeronomy are located. Those institutes are our scientific partners in the Asgard project. So we go there. We have the launch approximately at noon. Before that, we have some presentations that are given. We convene on the meadow where the launch is taking place. We do the countdown all together. And after the launches, I hit the road together with those people who fly biology experiments and need to recover the samples of their experiments as soon as possible after landing. But the other teams stay on site, and they have a quite varied scientific program. There's the possibility to meet with actual scientists so that students can familiarize themselves not only with the science being done in these institutes, but also with what the daily life of a scientist is like, which is something that they tell us they appreciate very much. Because if they're engaged in a project like Asgard, they're likely to be in their final or next to final year of secondary education. They're thinking about going to university, studying something that is science or technology related. They have had science for a number of years in high school, of course, but they're pretty much in the dark as to what a scientist fills his days with. So that's a good occasion for them to shed some light on those aspects of the life of a scientist. The Belgian Institute for Space Aeronomy has had scientific instruments on Mars on a number of spacecraft over the last few years. There are people at the Royal Observatory that are studying the sun and its influence on the magnetosphere of Earth, space weather related science and things like that. And we offer workshops and presentations to the students there so that their time in Brussels is well spent and that they get a lot of things to think about, to consider in their choice for tertiary education, but also in their general formation as scientifically educated youngsters. During the afternoon, I'm chasing these balloons. They fly where the wind takes them, which pretty much means that there's no telling prior to the flight how long it's going to take for us to recover them, if we manage to recover them at all. It happens, not very often, but it does happen that we fail to recover a gondola. We've had one landing in the North Sea. That was lost. We've had one disappearing in the Netherlands after touching down and losing the lid of the box. That lid apparently shed just enough weight for the balloon to lift again, and it was never seen since. On the other hand, we lost a gondola in 2018, and that was recovered just a few weeks ago when somebody found it while working in a private forest. So we do our best to recover those gondolas. We're usually successful, but teams participating should be aware that there is a risk of not recovering the hardware. It may land on the roof of a private building that we don't have access to. Any number of things can go wrong. They usually don't, but you should be aware that there is a risk. Okay, assuming that the recovery is successful, again, it usually is, but there are exceptions. We take the gondola back and we hand the teams back their hardware. That is usually done at the Hello Hostel. I'm going to say some more about that in a minute. We provide hotel accommodation for those teams who are not from Brussels. I mean, teams that come from the coast or from deep in Wallonia, teams that come from other countries, obviously, can stay at the Hello Hostel. It's a youth hostel in Brussels at our expense. So we offer 3 nights of accommodation for that. So I take the gondolas when I have them, I take them to the hostel, and we give the teams back their hardware so they can get to work Thursday late afternoon, evening, Thursday night, because on Friday, we reconvene at the planetarium. These are slides from workshops and the topics that are covered in the workshops. Skip those. More workshops, the solar telescope here in the lower picture. There's a meet and greet with Dirk Vriemhout also on Thursday afternoon. This is a recovery where we got a kind phone call from a farmer saying, I think there's something that belongs to you in my meadow. There were no cows or other animals, so no problem, but the box was on its side, but it was intact, so no problem. We have had recoveries in the northern part of France, near Valenciennes. We've had recoveries in the Netherlands. We've had recoveries in Germany. By less than a kilometer into Germany, but still it was across the border. So there's no telling how far the gondola will fly. But on Friday morning, we will expect the teams to reconvene at the planetarium and provide us with a new presentation. So probably going to bed early on Thursday is not going to happen. We expect a very short presentation, something like 5 minutes on Friday morning, giving us an idea of the first results. Obviously, some data take considerable data processing in order to draw the appropriate scientific conclusions from them. But a first rough idea, untreated data, a first graph where one of the axes is not quite in the parameter it should be, I don't know, air pressure as a function of time rather than altitude, things like that. But just to give the different teams some notion of how successful your experiment has been, and to show that if your experiment failed, you shouldn't feel too bad because there's others in the same situation. Usually the success rate is between 50 and 75%. Last year was extremely successful. We have had years where there were like, I don't know, a third to 40% of the teams having success. If you'll pardon me for the expression, shit happens and experiments fail, which is why it's important to communicate with other teams and make sure that you test appropriately in order to reduce the chances of failure to the lowest possible level, but accepting that spaceflight is hard. And anyone who has participated in a number of space missions or high altitude balloon missions will confirm that things sometimes fail. It happens. It happens all the time. You shouldn't feel bad about it. What you should do is try to figure out why it failed so that it doesn't happen again next time you try. Okay, these are examples of scientific posters. Again, whether it's horizontal or vertical, we don't really care. We want you to produce the poster because we believe it's a very good exercise for you in reporting on the results you have obtained. And of course, it's nice to see your work side by side with the work of other teams. It's also something that you can put up in your classroom to motivate the next generations of students. And it's overall a good lesson in scientific reporting, which is also part of the work of a scientist, of course. Okay, this is from, I don't know which year it was, it could be 3 years ago. A group photo we take at the exit of the planetarium when the campaign is all over. Usually by staying at the Hello Hostel with the other teams, friendships are made and contacts are, contact addresses are being exchanged. It does create contacts abroad, which from a viewpoint of scientific networking is a good thing. And as they say, it's not what you know, it's who you know. It's always good for these youngsters to have some friends abroad, I think, especially if their minds share similar interests. It also goes to show that it's quite a community every year that you would be part of. We have these campaigns with approximately 100 to 120 students. So that makes it, I think, a very interesting experience for those youngsters and something to remember for a lifetime. Which pretty much brings me to the end of what I wanted to tell you guys. I could go on for quite some time. There is a manual with technical details on the kind of batteries we are flying, on flight profile. That contains some graphs of what the temperature inside and outside the gondola looks like during the flight, stuff like that. If you still have questions after consulting the manual, you can post these on the Facebook group, which is our preferred channel of communication in the open. We do private communication also as well, of course, but open communication preferably through the Facebook group. I know students tend to consider that as the medium for old people, but then the preferred medium for young people changes all the time. And I think it's best to build in some inertia in there and not go with every new platform, be it WhatsApp or whatever, and changing all the time. Anyway, by keeping it on Facebook, we can also continue to reach out to former participants in Asgard, which has some advantages as well, because they tend to move on into the sciences and technology and gain experience that I or nobody in the Asgard program may have. Okay, I have spoken enough. I think it's up to you guys now. Let's see. I don't have templates for reports, Peter.
Okay.
We leave that up to the students. If something is unclear, I will contact them and ask for more details.
But could you maybe provide an example of a good progress report, Eric? It could help the teams maybe.
I would need to look that up, but I'm sure I have some. Cost of participation. Well, you need to come to Brussels. How much that is going to cost depends on your team size. I did not mention that during the presentation. We provide live participation to the Asgard campaign to teams of 5 students and a teacher. Some teams, especially the British teams, if they are mixed male-female students, they require 2 teachers because apparently a male British teacher cannot take care of female British students. So there's an exception for those kind of situations. But we do provide that. 5 students, no more, because we need to limit the number of people visiting the space pole, because these are research institutes and we can't have, like, I don't know, 500 people over there. We do not provide any money to teams. So we are offering you guys the hotel accommodation. Participation in Asgard is free. We have some sponsors that we are talking to at this time to provide you guys with some catering sandwiches and things like that while you are at the planetarium or at KMI, at the space pole in Uccle, where the launch takes place. But other than that, you guys are on your own. So that means that the cost of getting your team to Brussels, the cost of moving your team around in Brussels, coming to the planetarium from the hostel, going to the launch site from the hostel, moving around in Brussels if you guys wish to visit something in the evenings, those costs are on you, as are the costs related to your experiment. So it's quite difficult to put a number on that, because on your experiment you can spend anything from 20 euros to, I don't know, 2,000. The most I ever spent on an experiment was, I think, something on the order of 300 or 400 euros. That was our first gamma spectrometer, which was on the balloon that was lost in the Netherlands. So you can imagine my fury at that time. But most experiments are on the order of, I don't know, 100, 150 euros. The manual you can obtain from me or from the Facebook group. I think I posted it there. I did post the proposal form template on the Facebook group.
We will also publish it on the ESERO website about Asgard.
That is something definitely. How many proposals every year? It varies. I think in the past 7 years or so, we have not selected less than 12, and I don't think more than 20. It's something in between those numbers. Chances of acceptance are slightly over 50%. So we accept approximately half of the project proposals. One thing else I do is that if you are in time with your project proposal, you can pre-submit it. And time permitting, I take a look at it and I provide you with some feedback so that you can improve on your proposal before submitting the final form of it. The goal there, of course, is to avoid having to reject a project proposal just because some things were not thought well through, or because a beginner's team missed an important consideration. So we do provide that. The ratio between experienced and non-experienced projects in flights is very much dependent on the quality of the project proposals. It's usually no less than 1/3 for either group. So it goes from 1/3 experienced to 2/3 beginners to vice versa. Yes, you can submit several project proposals. We have a school that is so eager on participating that they submit 7 or 8 project proposals every year. Obviously, we try to maximize the number of schools participating in the project. So if you're submitting 8 projects, you should not be surprised if we only select 1. It doesn't mean the 7 others are no good. it could mean that the second or the first non-selected of your 8 proposals is an excellent proposal, but we just don't want to select 2 from one school. It happens that we do, but you should not count on it. Yes and no. I don't know what equipment your school has, but we can definitely do a vacuum test at my school. We have an 80-liter vacuum tank that should be, well, that is available now, and it's definitely going to be made available for Asgard. We will try to modify that facility in order to make sure that we can do a thermal vacuum test and not only provide a test under vacuum conditions, but also under cooled vacuum conditions. But generally, where things go wrong is the vacuum. It's far less a thermal problem, it's more a vacuum problem. Thermally, we try to keep the electronics inside the gondola where temperatures don't drop below -10. But of course, if you want to measure something outside, then the sensor should be outside. The gondola is made of styrofoam, so you can punch wires through the walls of the gondola, no problem. The gondola is not pressurized. So you will have vacuum inside, but the temperature will be kept between something like 30 degrees Celsius and -10.
Erik, I have another question.
Go ahead.
Because you have given us the time schedule of the current edition, and it was not fully clear to me what everything meant, actually. So at the 15th of January, you have the first progress report. That is very clear. But then you write at the 15th of March, you have the final design description. What do you mean with final design description?
I need to know by that time which hardware you're going to use. I especially need to know what the final mass of your experiment will be. And if you're using the Asgard batteries, I will need to know what your peak and average power consumption is going to be.
Okay.
I need to know the average power consumption because that determines how much batteries I need to provide. And I need the peak power consumption in order to know what fuse I'm going to use to protect your experiment and the battery from each other. We've had an experiment in the past that developed a short and that drained the battery for all the other experiments connected to that battery. That was very early in the Asgard program, but it has taught us that we need to provide individual fuse protection for every single experiment. Now, I can use a slow fuse, and I prefer to use slow fuses, but we will probably shift to a surface mount fuse protection this year in order to save on weight. So I would like the teams to provide me with both peak current draw and average current draw.
Okay, thank you. And then the next is the 30th of March, building phase for flight hardware.
Yep.
Do you mean the building should be finished at the 30th of March?
Ideally.
Yeah.
Ideally. So and they should definitely accord their schedules into finishing the hardware by late March. That provides some backup because things tend to go wrong at the worst possible time. I mean, those of you who haven't heard of Murphy, if you participate in Asgard, you will get to meet him. Things go wrong. Essential components are being burned. You need to order new ones. They don't come as soon as you want them to. You need to provide yourself with some buffer in order to still make the deadline for the submission of the hardware.
And then afterwards, the teams will test their experiment themselves at their own.
That is the ideal situation. Now, I understand if schools don't have an appropriate vacuum equipment, in which case I can test it for them. But it's not a good thing if these tests need to be done by the time we should be integrating. So the date for the delivery of the hardware should be done in the confidence that the testing showed that it should work, which means that the tests need to be done by then. And you can't test before your hardware is finished, so your hardware needs to be finished in time. And students have a certain tendency to postpone everything until the last minute. and beyond, they need to get rid of that attitude if they have it.
So, and how do most teams deliver their hardware? Because they have to deliver to the planetarium in Brussels.
Oh, they can do it to my school, or they can send it to my house. That is really not the point. How it is delivered doesn't really matter. They usually put it in a box with some styrofoam or bubble wrap or whatever, and they send it by mail, or they deliver it physically. Brussels schools tend to deliver it physically to the planetarium, or to my school, whichever is more convenient to them. Planetarium is very easy to reach. It's very near the Brussels ring. So those coming in by car can do it that way. The foreign teams just send it by mail. If you do deliver it to the planetarium, make sure you clearly label it as an Asgard project that should be delivered to me, because otherwise it ends up at the reception desk and they don't know what to do with it. And then I come to the reception desk and I ask if there are any experiments being sent in, and they tell me no, because they don't know it's about Asgard. So that should be clearly indicated.